Hello everybody. Let us try to understand the how to solve one-dimensional Schrodinger equation for quantum computing applications. Now, Schrodinger's equation is given by this equation as shown here. It is iota h cross by 2m del of psi with respect to del of t. This is the time derivative of the wave function, and this is equal to minus of h cross. It has to be no. This has to be square here. This is minus h cross square by 2m del square of psi with del square plus v psi. Now psi here is the wave function and psi depends on x and t. Now v in general also depends on x and t, right? V is the potential energy, psi is the wave function. Now this is the variation, this is how the wave function, the double derivative of the wave function with respect to position square, and this is the time derivative of the wave function. That's how the relationship is there as explained in the Schrodinger's equation. From what do we mean by solving one-dimensional Schrodinger equation is that we want to find out about this wave function so that we can know about we can know the information about the quantum particle, right? So in this point, the point to be understood from the beginning is that this wave function depends on x and t. V is also depends on x and t, but let us assume v does not depend on t. So let us for the sake of for the sake of getting the solution of the Schrodinger equation, let us assume that v does not depend on t. So therefore we can say that Vx comma t is actually Vx. Now in this case, this is a partial differential equation, and to solve the Schrodinger's equation, we will use the method of separation of variables. Now what is this method of separation of variables? This is the partial differential equation. We will turn this partial differential equation into two ordinary differential equations. That is, we look for a solution which is of this form. So we will try to use a method of separation of variables, and the solution will look like of this form. This is the wave function which is uppercase psi, which is the wave function which depends on x and t. Now we will we will use the method of separation of variables, and we will use small psi, which is a function of x, and phi and a phi function which is dependent on t. So this is a separable solution. We are looking for solutions that can be split into product of functions. So this is how we do the splitting of the main function into two smaller functions which are dependent only on x and t individually. One function depends on x and the other function depends on t. Now substitute this relationship of capital psi into, because in the Schrodinger equation this psi is actually this psi which depends on x and t both, right? So when we are trying to solve this using method of variables, we will substitute the value of this wave function with this separating solutions, right? So we will use capital psi equal to small psi into phi. So that's what is done by substituting this. So in this case, if you look at the Schrodinger's equation, here it is the time derivative. So that means here this phi function is dependent on time and this psi function is dependent on x. For this derivative, this psi x psi small psi is just like a constant here, so it's not a variable here. So that means we can take out psi from this derivative. but the second derivative is dependent on x. So from here we can take phi out. So phi is out. That's how this partial differential equation is turned into this form, where we have used capital psi to be equal to product of two solutions, psi and phi. Right. Now, taking the solution further, we divide this equation by psi phi. So once we divide it, we will get it equal to this. From here, this psi phi will cancel out. It will take this form. Left hand side, so if you see this equation, left hand side depends only on time and right hand side depends only on x. For any value of time or for any value of position x, left hand side must be equal to right hand side. That's what this equation tells us. The only way that can happen is if both left hand side and right hand side are constants, right? So in this case, what we can say that the left hand side will be equal to some constant independently and the right hand side will be equal to some constant independently. So we will get the modification of the previous equation like this. This is the left hand side, it is equal to some constant capital E, and this right hand side is also equal to this constant capital E, and this E is known as the energy. Now left hand side, so if you take out only the left hand side, so left hand side equating it to a constant capital E, so this is so that means we have turned a partial differential equation into an ordinary differential equation. So left hand side will give us one ordinary differential equation and right hand side will give us right hand side will also give an ordinary differential equation. Now let us let's first deal with ODE, that means the ordinary differential equation that depends on time. So let's consider first the case of left hand side equating to a constant E, capital E. So just modify this a bit, because this is not okay, let me just, this is actually wait a minute, this is actually d phi by dt. So if we take these things of iota, h cross and phi to the right hand side, we will get d phi by dt equal to minus iota e phi divided by h cross. Now this is the time derivative of a function. So therefore the time derivative of this function is equal to the function itself. That means this is the time derivative of the function phi. It is equal to the function itself, which is phi, multiplied by a constant, because e is constant, iota is constant, h cross is constant. The function that shows this kind of characteristic, what kind of characteristic? In which the time derivative is equal to the function itself. This type of function, the function that shows this kind of characteristic, is called an exponential function. So therefore, just modify this a bit, d phi by phi, it is minus iota capital E divided by h cross into dt. So if we integrate both sides, we will get the integration like this, right? So the solution of the integration, because this is all constant, this will give me t here with the solution plus constant term, and this 1 over phi integral will give me log of mod of phi. This is the solution of this integral, this is the solution of this integral. Now in this log of mod of phi, we need to make sure that this is the absolute value, because log can take only positive values. So that's why this mod function has come here. Now this further we exponentiate with e on both sides. So when we do the exponential, when we take the exponential, we will get it equal to like this. So this will be equal to e of minus iota e by h cross dot t plus c. and this constant e to the power c, we can equate it to some constant a, but we can absorb this constant because we are using method of separation of variables. So first we are using the variable function which is phi. So what I say is that this constant which is a, this can be absorbed in the other variable function. So we can absorb this a into other function because we are dealing with separation of variables, that is capital psi a small psi into phi. So we can move a from phi side to psi. So therefore we can move a from phi side to psi, and we can get rid of this a, and we can say that this function phi t, because this exponential and log will cancel out, we will get phi of t is equal to e to the power minus iota e capital E divided by h cross dot t. So this is the time dependence of each separable solution to that of the Schrodinger equation. This is the time dependent solution, right, of the Schrodinger's equation. Therefore we have an exponent with a negative imaginary factor. So this is the this is my imaginary factor iota e by h cross, negative imaginary factor, and the exponential is there. So this is the time dependent solution. Now let us consider time independent Schrodinger's equation. What is that? So let us consider this right hand side, and as I said, this right hand side will be equal to some constant capital E. So let us consider the second case, which is the time. So the second case is that we are equating second right hand side of the Schrodinger's equation equal to some constant, which is the equal to some constant capital A, which is basically the energy. This is another ordinary differential equation, but this ODE depends only on x. So we multiply throughout by psi. So what we get with the multiplication of psi, we get it equal to this 1 over psi will cancel out, right? We will get it equal to this. So this is termed as time independent Schrodinger's equation, and in short form we can write it to be equal to TISE, T-I-S-E. This is time independent Schrodinger's equation because there is no term which is specifically dependent on time, where this potential V can be whole range of, this V can be a whole range of potential energy functions. Actually the complexity of the solution will depend on what potential energy function we choose here, right? That's what I'm trying to say here. V can be whole range of functions depending on what V is. We have whole range of different techniques. Now this term minus h cross square by 2m of double derivative of the psi with respect to x is related to kinetic. This term is actually related to kinetic energy, and this is potential energy. We can prove this also, that this term is actually half mv square. So this is kinetic energy term, this is potential energy term, and this is my total energy. Now that's how this equation is there, time independent Schrodinger's equation. We have to solve this equation to find out what psi is, so that we can know about we can get information about the system from the wave function. Now Hamiltonian operator is the total energy. So kinetic. So what Hamiltonian operator I'm talking about? This is E psi. I'm calling it. We will deal with the Hamiltonian operator in detail in the coming lectures. But we can say that this is the Hamiltonian operator, which is the total energy. That means the kinetic energy plus the potential energy. And Hamiltonian operator is acting on psi. Here we will see that the Hamiltonian operator is actually the energy. I'm leaving it to further lectures, but we can say that the Hamiltonian operator is actually equal to is equal to E, and this E is acting on this wave function psi on the left hand side, and the right hand side is actually the sum of the kinetic energy and the potential energy. This is giving us back psi but with E. Now E is actually going to be the eigenvalue. So E will be, energy will be the eigenvalue. We need to know for what Vx we need to solve Schrodinger's equation. So we, as I just explained here, it is the complexity of this potential energy function that will actually define the complexity of the solution of the time independent Schrodinger's equation. Now what Vx we choose, accordingly we have to solve the Schrodinger's equation, but in general this is the Schrodinger's equation form, which is Vx plus this time independent Schrodinger's equation equal to psi x, right? Now psi x can be set of functions that satisfy this psi x I'm talking about. This can be set of functions that satisfy this Schrodinger's equation. So once we have psi x, then we can take general case of psi xt and write it in the following form, because in the previous case we have found out phi with the time independent, the solution from the time independent Schrodinger's equation we will find out psi x. So we have two solutions, psi x and phi t, and we started from the method of separation of variables, in which the overall big psi, which is dependent on x and t, so we will substitute for psi x and phi t. This is our phi t we have calculated, and this is our psi x. We will calculate from this equation, which will further depend on the potential energy function, as I just explained. That's how we can solve the Schrodinger's equation, and we will get the wave function value. Now these are known as the stationary states, right? So we have used method of separation of variables to, I will talk more about these stationary states, psi x, as we go along with the lecture. Now we have used method of separation of variables to solve the Schrodinger's equation. The solutions that we found are separable solutions, but not all solutions are separable. So let us again look at separable solutions. This is our separable solution. This is our phi t. Psi x solve time independent Schrodinger's equation, right? Separable solutions are stationary states. The question is how they can be stationary states when there is time dependence. As I said, the separable solutions, what are separable solutions? The small psi and phi, these are separable solutions, and I say that the separable solutions are stationary states. But the question is that why it can be stationary state when in phi t there is a time factor is there. The question is how they can be stationary states when there is time dependence, this factor t. Now wave function is changing with time, that is, it is oscillating in the complex plane, but this is the important point. Let's try to understand it properly. As I said, separable solutions are stationary states. The question is that how it can be stationary when there is time dependence, right? So that's the point of contention here. Wave function is changing with time. So this wave function is changing with time, with the presence of this t. That is, it is oscillating in the complex plane, right? Wave function is changing, but the probability density function that we get from wave function, how do we get? It is the mod square of the wave function. That's how we calculate the probability density function. But the probability density function that we get from wave function does not depend on time. The PDF is defined as the square modulus of psi xt, and this can be calculated using psi star psi. This is the conjugate of psi. This is how we can calculate the probability density function. Now if we try to calculate this modulus square of psi xt, so this is equal to psi star psi. So we have the value of psi we have. What is psi star? We have to take the conjugate over of this function. So how do we take the conjugate? It will be psi star and this minus iota will be converted to plus iota. This part is psi star. This psi is actually big psi. That means this psi is dependent on x and t. So this is the conjugate part, this is the without conjugate part, and if you look at the exponent, these two exponents will cancel out and we get the probability density function. So about the stationary states, wave functions are changing with time, but the probability density functions do not change with time, because when the exponent factors will cancel out, so there is no time dependence left in that case. So therefore wave function changes with time, but the probability density functions do not change with time because they cancel out. So therefore stationary states, so therefore the separable solutions are stationary states. So that's what is done here. PDF does not depend on time, is a stationary state, so is equivalent to these are just the points that I'm trying to explain, that that the absolute value square of the wave function is a stationary state, that is this function, that is the absolute value square of psi x only is equivalent to probability density function. This is probability density function, this is also probability density function, right? And this is equal to this. So therefore we are dealing with a stationary state, because the exponent factors will cancel out, because the probability density function does not depend on time, though wave function changes with time. So therefore we call these separable solutions as stationary states, right? In the further solutions of Schrodinger's equation, we will talk more about the Hamiltonian operators and how these Hamiltonian operators can be used in the solution of the Schrodinger's equation. Thank you.